Bismillahir Rahmanir Rahim. In the name of Allah, the most beneficent and the most merciful. Welcome you all again in the virtual learning system of Pakistan International School Taif, Saudi Arabia. Dear students, as you know that this is Pakistan International School Taif virtual class for class 10 student subject computer science, and today is our 31st lecture. Teacher name Imran Ahmed. Dear students, as you know that in the previous lecture we were discussing about the C language. Next chapter is chapter number 6, which is in the reduced syllabus. It has some topics. Chapter number 6 is computer logic and gates. This chapter belongs to the electronics of computer science. Now we will discuss about the computer logic and gates. First topic is data representation in computer. Very easy. This chapter is very easy because as you know the data representation is in the computer is based on the 1 and 0. Okay, computer is an electronic machine and it consists of millions of electronic switches. An electronic switch is very similar to an electronic switch that is used to turn on or off light. When you put on the light, so it means that 1 represent the on and 0 represent for off. The main difference is that it works on very low voltage. If the electronic switch is closed, electricity flows and it's open. Electricity does not flow. The switch has only two states. As you know that every button has two states, either on or either off. So on represent 1 and off represent 0. Binary number system used for the counting also consists of the two digits 0 and 1. Therefore, binary digits 0 and 1s are used in computer to represent two states of a switch. When current flows in a switch, it is on. It means that its state is 1 and represent binary 1. When there is no current in a switch, when you put on the bulb, it means that there is a current inside, so it is 1 or it is on. When the switch is off, it means that it is in 0 state, or you can say that it is off state. So a binary digit 0 or 1 is referred to as a bit binary integer. Groups of ones and zeros are used in computer to represent data, and this is known as binary code. For example, the binary code 1 0 0 0 1 0 0 may represent the letter D. Why it is representing the letter D? As you know that the ASCII code of capital A is 65 and the B is 66, C is 67, D is 68. So you can convert the 68 into binary form and you will get this result. A computer must be able to recognize codes that represent numbers. So as you know that we are dealing with the numbers, letters and the special characters. These codes are known as alphanumeric codes. Alphanumeric codes means, let's say a character is F underscore 16. So alphabets is there, special character underscore is there, 16 numerics is there. So this one is called the alphanumeric. Alphanumeric codes include the following letter: lowercase letter A to Z, uppercase letter A to Z, numeric digits 0 to 9, and special characters. Many special characters are there, such as percentage, dollar sign, address, hash, plus, etc. The American Standard Code for Information Interchange ASCII is the most commonly used alphanumeric code. It is 7 bits to represent a character and total number of character, it is in 128. So ASCII is 7-bit code. Sometimes we can use the ASCII as 8-bit. So ASCII is 7-bit code. So ASCII is American Standard Coded Information Interchange, is the most commonly used alphanumeric code. It uses 7 bits to represent a character, and the total number of character it represents is 128. As I told you, watch here, the character D is representing digit. How many? 1, 2, 3, 4, 5, 6, 7. So this D is representing in the ASCII. How they represent this one? I told you the ASCII code of capital A is 65, B 66, C 67, and D is 68. So you can convert the 68 into binary form. When you convert this, digits will becomes at the front of you. The result of 68 in the binary form is this one. So now this digit will be transferred in the electrical circuits. The circuitry of the digital computer works on the DC voltage, such as voltage can have only two possible values at any time. Figure 6.1, watch here, this figure is representing. Now to understand this figure, so 5 volt is the maximum and the minimum is the low voltage is 0 voltage. So the line which is representing highlighted at the bottom is 0, and the line at the maximum 5 volt represent the high volt. So this one I can say that 0, 1, 0, 1, 0, 1, 1. So this one is the representing of the letter digit. Next, just next topic is digital logic and the logic gates. Very interesting and very easy topic. Digital logic is the fundamental in creating electronic devices such as calculator, computer, digital watches, etc. So digital circuits are used and such kind of devices. It is used to create digital circuits, which consist of a large number of logic gates. So which consists of large number of logic. Now we will discuss what is a logic gate in the physics. Although you have studied, I hope you have studied these topics, but over here just for the introductory level, this chapter belongs to the electronics of the field. Now what is logic gate? Are the building blocks of digital circuits. A logic gate perform a particular logical function. Logic gates has two or more logic inputs. I will tell you how many inputs are two or more, how why I'm saying there. That is two or more, so low or high, and produces a single output. So input can be two or more, but the output should be only one, which may be low. So output should could be low or high, determined by the logic levels presenting at the input. Basic logic gates. How many logic gates are used? Watch here. First one is the AND. There are three basic gates: AND, OR, and NOT. In the C language, already we have studied the logical operators. Same concept, but in the form of diagrams. Now we will represent the AND, OR, and NOT. So AND gate. Watch here, the symbol used for AND gate is D shape. So D shape is AND gate representing. The AND gate has two or more inputs that can be low, zero or high. Already we have discussed the truth table for the AND gate. So watch here, when the input is zero, low means where the word is zero. So it means where the word is zero or the word is low, there it means that off or zero state. So low or low, output should be low. Watch here, output should be low. Low or high, output low. High or low, output is low. High or high, output is high. This is the same truth table, when I tell where I tell you when the input in the concept of AND gate, there should be, when you achieve the high input output, so all the input should be high. It means that if any condition becomes false, so its output should be low. AND gate has the two or more inputs that can be low. Low means zero or high means zero. So I can represent 0 0 0 0 1 0 0 1 0 and 0, and when the input becomes 1 and 1, its output should be 1. The logic operation of two input AND gate is shown in the figure 2.6.2. This one is the 6.2 figure. Now we are going to represent the OR gate. The symbol used to represent the OR gate is this one. So place the, you can say that the this symbol is look like this curve shape D. First the D or any other symbol, but over here there is a curve. In the AND gate there was not a curve. Over here OR gate there should be used the curve. So the same concept I told you in the, when we were discussing about the OR operators, when any input becomes one, when any condition becomes true, its all result will be one or true. So watch here. First one, low or low result is low. It means that there is no true or the no one is there. So output should be low. Low or high, high, you can say that 0 or 1 result is 1, or 1 or 0 result is 1, or 1 or 1 result is 1. The OR gate has two or more inputs. The output of an OR gate is low only when it becomes low, only when all the inputs are low. The output is high when one or more of its inputs are high. The logic operation of two input, watch here, there are two inputs and the one output is there. Third gate, the basic third gate is the NOT gate. As we know that the NOT gate, NOT operator is used for the negation purpose. The NOT gate performs the function of inversion. Therefore, it is also known as inverter. It has the single input. The output of the NOT gate is high when the input is low and the vice versa. So watch here. The symbol which is used for the NOT gate is this triangle. At the edge of there should be a circle, small circle. So this may represent the NOT gate. So not when the input is low, when it passes to the NOT gate, it becomes high. But when the input becomes high, when it is passes to the NOT gate, it becomes low. So this is the major concept of the NOT gate. Next one is truth table. A truth table represents the digital circuits in table form. In the table, how to create the truth table, I will tell you. It shows how a logic circuit's output respond. Let me small little bit. To all the possible combination of the input using logic 1 for true and the logic 0 for the false. It has the following properties. Number one, truth table consists of rows and columns. Watch here. This one is the truth table is present. There is rows and there are the columns are in the form of vertical lines. There are columns in the form of horizontal lines. They represent the rows. It shows the relationship between input and the output from a digital logic circuit. So on the basis of digital logic circuit, we can represent the inputs and the output. It shows output for all the possible combination of the inputs using 0 for low and 1 for high. When we create a table, truth table, so this one much easy for you. And all the combination of inputs are listed in the columns. on the left and the output is shown on the rightmost column. So this one is the input side and this one is the output side. The input columns are constructed in order to binary counting with the number of bits equal to the number of inputs. So keep in mind, number of bits must be equal. Why they represent the 0, 0, why this comes is the 0, 0, 0. So over here, I will explain in the after the properties. Each row of a truth table contains one possible combination of inputs and the result of the operation for those values are shown in the rightmost column. Now I am going to create a solve a simple question which belongs to the truth table. I will show you how to make the truth table. Consider the truth table of the digital circuits as shown. They give us the example. So how to make the truth table? Watch here. X, Y, and Z. There are three variables are there. 2 raised to power 0. When there are three variables, so you represent 2 raised to power 0, 2 y becomes 2 raised to power 1, x becomes 2 raised to power 2. So x, y, z, so I start from the leftmost side because there are three variables truth table. 2 raised to power 0 is equal to 1, 2 raised to power 1 is equal to 2, 2 raised to power 2 is equal to 4. Now when the input becomes 0, now this input must be equal to the this weight. Input should be equal to the weight. Now when the input is 0, so it represents 0, 0, 0 because there is no, if I take the 1 over there, so it will be 1, weight will be not equal to the input. So we must equalize the input with the weight. When the input is 1, now what happened? 0, 0, 1. Watch here. Why I put this one over here? Because 1 is equal to 1. This input is 1 and over here this input is equal to 1. So weight is equal to the input. So that's why I place the 1 over here. Rest of the bits will be 0. Now when the input is 2, watch here. 2 is over here, so 2 is equal to 2, so this one is 0 and the 4 bit will be 0 and the 1 bit will also becomes the 0. When the input is 3, now we want to equalize the input with the weight. So 2 2 plus 1, 2 plus 1, 2 plus 1, so which bits are used? Y is used and Z is used, so Y will become 1 and Z will become 1. So 3 is equal to 3. So this one 2 plus 1 is equal to 3. Now when the input becomes 4, 1, so 4 is over here in the X, so this one will be become 1. When so these two bits will become 0. If I put the 1 over here, now this will becomes the 5. 5 for the input. When the input becomes 5, 5 is equal to, watch here, 4 plus 1. Which bits are used? X is used and the Z is used, so I place the 1 for the X and 1 for the Z, so Y becomes off. When the input becomes 6, so for the 6, 4 bit is used and 2 bit, where 4 plus 2 there will be 6. So 6 for the 6, 1 1 and the 0 is over here. And when the input becomes 7, watch here, which bit will be used? 4 plus 2 plus 1, so there the output is 7. So 7 is, all the 3 bits are used, 1 1 and 1. So to make the 3 bits variable, now 3 bits truth table, 3 variable bits for the truth table, this logic circuit will be used. Which one? So this one will be used for the 3 variable logic circuits. Now watch here, for the, they didn't show the inputs of 0 1 2 3 4 5 6 7. That's why I show you the another question and I make the truth table for the you. So why this is that this one is output, I will, this one we will discuss why this one f is a 0 or the 0 0 1. So I will, they are showing over here. The which operation, they didn't give us the any consider, they say the consider digital circuit. So they didn't give us any equation for this purpose. Yes. Next topic is logic gates and their truth tables. Now we are going to develop the logic gates and the truth table. As I told you, there are three basic logic gates: and, or, and not. So all the rest of the logic gates derived from the and, or, and the not. So major we have three basic gates. The commonly used logic gates are and, or, NAND, NOR, NOT, exclusive or, and the exclusive NOR. So we will discuss these logic gates. First one, AND gate. As I explained in the previous, the basic gate, AND gate, the truth table, because there are two variables are used, x and y. Watch here, if y is 2 raised to power 0 and x is 2 raised to power 1. So what will becomes the output? 1 and 2. So there will be 4 input. 2 raised to power 2 is equal to 4 input will be there. This one is for the 0 input, 1 input, 2 input, and the 3 input. The AND gate operates such that the output will be the at level high only when all the inputs are 1. When all the input, watch here, when in this one, over here 1 is there, over here 1 is there, 1 and 1 result will be 1, and the logic gate which is used for the AND is D-shaped, and there are two variables, two inputs are there, and they are generated the single input. So when these two inputs will be passed from the AND gate, it will be x dot y, or you can write this one is xy over there. Similarly, for the OR gates, the symbol which are used for the OR gate is over here. So when the two inputs x and y, x or y will be passed from this gate, so it will represent x plus y. So they will represent x plus y. Now for the NAND gate, NAND stand for not and. Not and at the front of AND gate, if I place this circle, so it will make the not and, or you can say that NAND gate. And the truth table for the NAND gate is this one. Watch here, it is the negation of the and having the input 0, 0, 1, and the NAND having the input when I apply the complement, let's say F complement is equal to, so it will be 1, 1, 1 and 0. Where the 0 is there, so there will be 1, and the when where the 1 is there, so it will becomes 0. So watch here, we apply the NAND operation on the AND. So the gate will be called the NAND operation, and its output will be x dot y, and the complement is over there. They shows the NAND operation. Similarly, for the NOR gate, NOR stands for not or. Not or, how to represent the not or? When you pass any two inputs variable from the OR gate, so output becomes x plus y, but this one is the NOR gate, and you place the small circle at the end of NOR. So f is equal to x plus y and the complement. So how this input is over there, where there is 0 and it represent the 1 over there. This one, the watch here, this one was the truth table for the OR gate. Over here only 0 was there. This will converted into the 1, and rest will be converted into the 0 state. So these are the NOR gates. Next one is NOT gate. As you know that NOT is the negation of the input. So if the value of x is, if the value of x is 1, it will convert into the 0. If the value of x is 0, it will convert into the 1. So when x is passes from the NOT gate, it will be the x complement. Next one, exclusive exclusive OR gate. Exclusive OR gate represent, watch here, this is OR, and before the OR there is another curve line. So this one, another curve is there. So this makes the exclusive OR gate. So exclusive OR gate has the graphic symbol similar to that of OR gate, except for the additional curved line to the input side as shown. It produces one output only when the two inputs are at the different logic levels. Its output expression is f is equal to, so this one is the constant over here for the two variable x y complement plus x complement y. So this one will be the output for the exclusive OR gate. Similarly, exclusive NOR gate, exclusive NOT and a NOT is there and NOR is also there. There is a exclusive NOR gate is the complement of the exclusive OR gate as indicated by the small circle on the output side. The graphic symbol it produces the one output when the inputs are at the same logic level. Same logic level, that is when the both input 0 or both are the 1 as shown in the figure. So it's constant equation for this one, f is equal to xy plus x complement y complement. So this equation represent for the exclusive NOR gate. Creating. So how to create NAND, NOR, exclusive OR and exclusive NOR gate using the basic gates. So we are going to create the basic gates. How many basic gates are there? There are three basic gates, and now we are going to create these three basic gates. One is AND, uh, OR and NOT. So these are the three basic gates. First one, we are going to create the NAND gate. So how can NOT and, as I told you, NOT AND. The NAND gate can be easily created by using AND gate and NOT gate as shown. Watch here, there is AND gate and there is NOT gate. So simply you can write this one is D and small circle over there. So they are making the NAND gate. Similarly, for creating of the NOR gates, how to create OR gate and NOT gate, they will make the NOR gate. Creating exclusive OR. So how to exclusive OR and exclusive NOR gate using basic gates. So how to create this one? To representing the, as I told you, the equation used for the exclusive NOR gate is, exclusive OR gate is this one, x y complement plus x complement y, as the this one is used for the exclusive OR gate. Now watch here how they are making with the with the help of basic gates. X y, there are two inputs and we are going to create, let me a little bit more visible to you. We have the equation for the exclusive OR gate one, this one, x y complement plus x complement y. To create this equation with the help of basic gates, watch here, this is the x input, this is the y input. So first one is x and y complement. First x is going over here at the top line, x is going over here, and y complement. Watch here, this straight line, when it passes from the NOT gate, so it will becomes the y complement. Now x y complement is passing with the xy complement is passing with the AND gate over here. They are drawing the D over here at the top D. So xy complement is coming from the this side and or till over here. Now second operation is x complement y. Now same input. Watch here at this black dot spotted top, the black dot spotted, the x is coming over here and it is passes from the NOT gate, and over here after passing the NOT gate, it becomes the x complement. So next one y. So y is simple input to the AND gate. Now these two are x y complement and plus x complement y. So this one is the creation of x complement. So watch here, x y complement is passing from the OR gate, plus represent the OR gate, and they are using the OR to representing this one. So this one is the creating of exclusive OR gates. Next one is the exclusive NOR gate. The equation, the function used for the exclusive NOR gate is xy plus x complement y complement. We have equation f is equal to xy plus x complement y complement, this one representing the exclusive NOR gate, and we are going to convert. First we will solve x dot y. First one is AND operation x dot y. So simple input x and simple input y, when processed with this gate, this symbol, so they are making the AND operation x to y. Now after that, x complement y complement, when the x is passing, watch over this line, when x is passing from the NOT gate, it becomes x complement. When y is passing from the NOT gate, it will becomes y complement. Now the input of x complement and y complement in the D symbol, this AND gate, so they will make the x complement dot y complement. When the both xy and x complement y complements are passes from the OR gate, they are going to make the xy plus x complement y complement. So this is the simple equation for the exclusive NOR gate, and this is the logic circuit for the exclusive NOR gate. Little bit. Conversion of the Boolean function to a logic circuit. Now in the equations, they give you any simple equation, and you will they will ask to convert this one into the logic circuit. Conversion of watch here, as you aware of the now AND gate, OR gate, NOR gate, so you can convert into easily with the help of these gates. You can make the easily make the logical circuits. You can easily make the logical circuits. Conversion of Boolean function to a logic circuit. First of all, we will discuss what is a Boolean function. Is an expression formed with the binary variables. So the logical operators OR, and NOT gates, parentheses, and the equal sign. A binary variable can take the value 0 or 1. Let's say there is an equation is there, f is equal to x plus y. Watch here, there are one function is over here, f is representing the function, equal sign is there, and two binary variable, one is x and another one is y. Not it is restricted for the two variable, there could be three variables and four variables, five, but your course representing the up to three variables, you can create this one. Now we are going to the first example, conversion of the Boolean function. For example, we have the Boolean function f1 is equal to x, y, and z complement. So watch here, the operator between these three binary variables are AND operators. Why I'm saying? Because x multiplied by y multiplied by z complement, not a z complement. So now over here we are going to convert this Boolean function into the logical circuit. How to convert? I will tell you how to convert this circuit. As you know that the equation was x, y, z complement. X and y are simple, means there is no complement at the x and y, but there is complement on the z. So x, y is simple, and z, when z passes from the not operator, it becomes z complement. So x, y and z, all of these three binary variables having which operations? And operation, because they are multiplying. As I told you, the dot operator represent the and operations, x dot y dot z. So you can write this one x y z complement. When there passes with the and gate, it will give you the same equation. F1 is equal to x, y, and z complement. I think today enough, and inshallah tomorrow we will discuss, and tomorrow we will finish this chapter. Tomorrow we will having the last lecture, and we will discuss also the exercise question answer. Till take care of yourself. Pray for me. Pray for all Muslim. Allah Hafiz.